Welcome to the first video on ellipses. This is the third conic section that we've talked about. An ellipse is in an elliptical shape, and I've given you some examples here, some pictures I found of ellipses. Okay, the cat thing is really stretching it, but this is an ellipse, and I just thought that was very interesting. Football stadiums are often elliptical. It's a pleasing shape, and it allows more people to be closer to the action. This right here was some interesting architecture, as well as this type of building was very interesting. Johannes Kepler lived in the 16th century, and he came up with Kepler's laws of planetary motion, which have been around since 1609. And shows that the ellipses are the paths of comets and planets around the sun, or moons around planets are often ellipses. And so you see here that an ellipse has a major axis, the long major, and then a shorter minor. It has a center, and it has two foci. Focus, singular, foci, for plural. And then here you can see that in an elliptical shape, the sun is actually located at one of the foci. And the planet is what goes in this orbit around the sun. So as you can see, there are times when we are closer to the sun and when we're further away from the sun. And so that's what happens with an elliptical orbit. Now, if I remember, I will show you what this looks like in class. But to draw an ellipse, you can actually tape a string, one end at this focus, another string the other end at this focus, stretch the string out with a pencil, and then if you could follow along, held in place by the string, it would actually form an ellipse. So putting this distance, right, is always this plus this is always going to be the same distance because it's the same string. And as you move it around this focus, you will actually draw an ellipse. It's pretty interesting. And they have names. Look at this. Aphelion and perihelion. And I'm not sure where they got those names, but this has to also do with the planetary motion. So the sun would be at a focus. See right here? So this distance to the planet and then to this would always be the same amount all the way around the ellipse. So here are the formulas, the standard equations and properties of an ellipse. You can see here that the long part is called the major axis. On this particular one, the x-axis is the major axis. This is the minor axis. You know, in an ellipse, it's always either wider in one direction or taller in another direction. The center of the ellipse here, so it's symmetrical, right? You've got symmetry here and here. The distance from the center to the vertex is A, always A, and so that means that from one vertex to another would be 2A. So if you know the distance from one vertex to another on the major axis, you could find A very easily. B would be the length from the center to the co-vertex, or the vertex on the minor axis, the shorter side. So then this minor axis would be 2B. So that's where you get the B. And then the length of the foci are always on the major axis. So foci and vertices go on the same axis. That's important. Foci and vertices are on the same axis. They're always on the major. And the distance from the center to a focus is C. C long. So then from focus to focus is 2C. So A, 2A, B, 2B. Okay, so here with a center at 0, 0, this is the general equation of an ellipse. So I have x squared over a squared plus y squared over b squared equals 1. A squared is always the bigger number. A squared is always the bigger number. And whatever the bigger number is under, that tells you the major axis. So because a squared is under x squared, it is the major axis. Now, this is an a squared, this is a b squared. How do you find c squared? Well, this is the relationship between a squared, b squared, and c squared. It is not the Pythagorean theorem. It is not. We don't have any right triangles here. It is not the Pythagorean theorem. But this is the relationship. So if I know a squared is always biggest, right? I subtract from it b squared, then I will find c squared, which will give me the length of the focus. Eccentricity. Eccentricity determines, it's a property of conic sections that determines how close it is to a circle. So the eccentricity for an ellipse is c over a. And so the closer it is to 1, the more circular it will be. Okay, so this is a circle, right? And this is an ellipse. So here's an example of an ellipse, an equation of an ellipse, so that we can graph it. So we have x squared plus y squared equals 1, and then we have the 16 and the 9 in the denominator. So we know that this is the larger number, so a squared is equal to 16. This is the smaller, so b squared is equal to 9. So that would mean that a is going to be equal to plus or minus 4, because I'm going to take the square root, and b is going to be equal to plus or minus 9. Now, not 9, 3. Sorry. Now, the reason that I have plus or minus here, right, you take the square root. The minus here doesn't mean it's actually a negative distance. It means that it's the direction. So there will be 2 points for each of those. To find c squared, I'm going to take 16 minus 9 and get 7. So c is going to be plus or minus the square root of 7. Now I can estimate that. I know what the square root of 4 is, right? That's 2. And I know the square root of 9, that's 3. So the square root of 7 is going to be somewhere between 2 and 3, closer to 3. And I can estimate. So to graph, I have the center at 0, 0. I know this because x squared and y squared. So the center is at 0, 0. The bigger number is under x. So I'm going to go 4, 4 on the x-axis. And those are my vertices. So this is a vertex, this is a vertex. The co-vertices are up and down 3. And I'm going to go ahead and draw in my ellipse. And all I have left to do are the foci. So it said somewhere between 2 and 3. So here's a focus. Here's a focus. Okay. And so if I'm listing them, these are co-vertices, right? The vertices are going to be at plus or minus 4, 0. The foci, same axis, plus or minus the square root of 7, 0. And the co-vertices are going to be at 0, plus or minus 3. And so we've done everything we need to do. We're staying organized, and we have our ellipse centered at the origin. Eccentricity, if you'll recall from the previous notes, said that eccentricity is c over a, and that's going to be the square root of 7 over 4. Now, the bigger the number, the further away it is from 0, the least circular it is. So if you were to find the square root of 7 and divide that by 4, you're going to get 0.66. That's not very far away. And so that's going to be an ellipse, an eccentricity with the ellipse. On the next example, you can see that we are not centered at the origin. So this time, the center of the ellipse is going to be moved or translated over 4 and down 1. So you'll notice that it's going to be the same number, but the opposite sign in there. Further, this time, the bigger number is under y squared. So once again, a squared is 25. B squared is 16. C squared is going to be 25 minus 16. You don't have to write it. I mean, you can see it from here, but that's 9. So A is plus or minus 5, B is plus or minus 4, and C is plus or minus 3. So what I like to do is go ahead and sketch a graph. It's easier to pull the points off the graph than it is to come up with them with some kind of formula. So the first thing I want to do is I want to graph the center. So I'm going to go 1, 2, 3, 4, down 1. And that's the center of my ellipse. Now this time, because the bigger number was under the y, I'm going to go up and down 5. So 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. And that's going to be my vertices. Those will be my vertices. That's my center. So the foci, or C, is going to be on that same axis. So I'm going to go up 1, 2, 3, and that's a focus. And 1, 2, 3, that's a focus. I need the co-vertices, so from the center, I'm going to go right and left 4. 1, 2, 3, 4. 1, 2, 3, 4. And then I'm going to draw that in. So I need the co-vertices to finish off the ellipse. And the only thing I have left to do is to find the actual points. So I can look here. It's going to be over 1, 2, 3, 4, but up and down, so I'm going to have, one of them will be at 1, 2, 3, 4, 4, 4, and 4, where's this one? 1, 2, 3, 4, 5, 6, negative 6. Okay, so if you're thinking about that, that's going to be the x-coordinate stays the same, that's a 4, right? And the y-coordinate, you are adding 5 and subtracting 5 from the y-coordinate, and that's how you get the vertices. So these are the vertices, but all I had to do was just pick them up off the graph. If your graph is pretty accurate, you've got it. All right, the co-vertices are going to be in the opposite order. So that means that they're going to have, both going to have negative 1, right? They're going to be at negative 1. But the x-coordinate is going to be 4 plus 4 and 4 minus 4. So you can see here it's going to be 0 and 8. Now we need the foci. The foci are going to be in the same order as the vertices. So these are both 4. And this time, the vertices are going to be the x-coordinate plus 3 and minus 3. But I can find it. So this is 4, 2. And 1, 2, 3, 4. So negative 4. Does that work? 3, negative, yes. So those are my points for this one. Eccentricity is C over A, which is 3 over 5, which is going to be less than 1. So it's getting very circular, but not quite. And look at it, it's pretty, almost circular. One more example. This one, they give us the vertices, the location of the vertices, and the foci, and they want us to write the equation. Well, if I look at this, if I sketch a quick graph of it, right, if the vertices are plus or minus 4, 0, and the foci is at 3, then this is going to be one that goes this direction. And it's also centered where? Well, it's centered at 0, 0. So far I know that it's x squared over something plus y squared over something equal to 1. Further, I know that the major axis is x. So this is going to be a squared, and this is going to be b squared. Okay, so far I know A, the vertices, and I know C. I don't know B, but I need it. So if A is plus or minus 4, then A squared is going to be 16. If B, sorry, not B, C, I don't know B yet. If C is plus or minus 3, then C squared is going to be 9. So far I know A squared, that's 16. I need B squared. Well, remember, C squared is equal to a squared, the bigger, minus the b squared. Or I could say b squared is equal to a squared minus c squared. Do you see that algebraically? Subtract the c, add the 1, you got the same thing. So I've got 16 minus 9 is b squared. Now, do I need the square root of that? No. So I just write 7, and I've got it. Okay, so in class, we're going to be doing some examples probably up on the board. So be sure you've taken these notes and gone over these examples and see if you can recreate it. This is not a very good graph. It's just a sketch. I just used it to help me solve the problem. So I'll see you in class.